Greetings, everyone. My name is Dr. Stephen H. Williams, and I'm coming to you today as part of my application package to join the Viking Speakers Program. I'll be giving a shortened version of a talk that I presented for the 2024 total solar eclipse, and it's called The Things Astronomers Learn When Things Go in Front of Other Things. Total solar eclipse is when the moon goes in front of the sun, but there are other examples too, as we will see. Back in the 1800s, people were observing total solar eclipses, and they noticed that just as the last little bit of the sun's surface disappeared behind the moon, they saw colors that they didn't normally see. And when astronomers or chemists see colors in light, they get excited because that usually means that there's chemistry there. And that's what happened here. In 1868, they looked at this more closely, and they saw lines in the spectrum like this. Here's the sun spectrum here and here. When they looked at different locations, they saw lines that corresponded to specific elements. And they also saw a set of lines that didn't correspond to any known element. They had discovered a new element in the sun, not on Earth. Well, what would they call this? Well, it came from the sun. Helios was the god of the sun. They called it helium. A new element that wouldn't be discovered on Earth for several decades later. Now, another thing that came out from total solar eclipses was an observational support evidence for Einstein's new theory of relativity 125 years ago. Einstein predicted that the sun's gravity would be strong enough to bend slightly light that goes past it, so that a star here would appear to be over here as seen from the Earth. The problem with that is it's a tough measurement to make, to confirm. You're trying to see a faint object next to the bright sun. No chance of doing that unless the sunlight were blocked by an object in front of it, the moon, in a total solar eclipse. When that was done, it worked. And on May 29th, 1919's total solar eclipse, Arthur Eddington took pictures that made the measurements that showed that Einstein's prediction was correct. Now, a total solar eclipse is not the only time astronomers learn things when things go in front of other things. All right, here's an example. This is the constellation of Perseus, the great Greek hero, slayer of Medusa, rider of Pegasus. And there's a star where this arrow is pointing right here that's different than all of the other stars in the sky that you can see with the naked eye easily. Now, people back in the olden days were familiar with the night sky. They were familiar with the movement of the sun, the moon, the planets. They were familiar with the daily and nightly movement of the stars across the sky. But what they weren't familiar with was something that changed in brightness. And this one star changes in brightness regularly. They actually crafted the constellations to put this star, Algol, at the head of Medusa, the Gorgon, the head of the demon. And that's what in Arabic the star's name was, the head of the ghoul, the head of the demon. We know today that it's not Medusa winking at us. It's actually two stars going around each other like this. And we just happen to lie in the plane of their mutual orbit. That means that periodically one star will pass in front of the other, eclipsing it. And instead of seeing the light of both, we see only the light of one. That causes a dip in brightness. And here's a graph of that. This is with time, this is brightness. And you can see when these stars get in the way of each other, depending on how bright they are, you get a significant dip in brightness. These are called eclipsing binaries. And you can learn a lot from them. I won't go into the math here, But depending on how deep those little eclipse drops in light are, how wide they are, their shape, you can tell a lot about the two stars without ever actually seeing the two of them together. Now, let's look ahead to the solar system. In the late 1700s, astronomers had figured out from trigonometry how big the solar system was in terms of the Earth-Sun distance. But they didn't know the Earth-Sun distance in miles or kilometers or things like that. So they didn't know the actual sizes of the solar system. But there are times when Venus passes in front of the sun. It's called a transit because Venus is so much smaller than the sun in its apparent size. And mathematicians like Edmund Halley figured out that if you observe that transit and accurately timed when it passed in front of the face of the sun from many different locations, you could calculate using trigonometry the actual Earth-Venus distance, which would then give you the Earth-Sun distance and all of the other distances in the solar system once you had that calibrated. This was the first time there was a major international scientific effort. It was for the 1769 transit of Venus. Captain Cook was sent on the first of his great voyages of exploration to Tahiti to make these observations. The place where he did so is called Point Venus to this day. The problem was the chronometers of the day weren't accurate enough, precise enough to give you the calculation precision that you needed to make the calculation. It works, it's just they didn't have the right equipment sensitive enough. Nowadays, we've got that equipment in abundance, and instead of it being a breakthrough in astronomical science, it's now left as an exercise for the student, and it's a darn good one. Now, we also learned more about the solar system when we started sending spacecraft out to them. The very first one that we sent successfully to Mars was called Mariner 4. It went back in 1964 to the Red Planet. It carried some primitive cameras and some other instruments, and it gave us a good close look at small parts of the Martian surface. Unfortunately, they were unusual parts, and we made assumptions about Mars all being that way that were later rectified. But there was another thing that was done, as only NASA can do, on the way to Mars. The radio guys who were controlling the radio that sent data back realized that the spacecraft's trajectory would take it directly behind Mars as seen from the Earth. Okay, so Mars is going to come in front of the spacecraft. And if the spacecraft sends a steady radio signal back to Earth, as that happens, as it comes to Mars, the Martian atmosphere would attenuate that signal. It wouldn't clip it off right away. They made the measurement, and they found that, yes, Mars did have an atmosphere. But it was much thinner than most astronomers had predicted. It's only about a few percent of what we're breathing here on Earth. So if there are any John Carters and Tars Tarkases and princesses of helium, oh, there's a giveaway, then they're not breathing very much because the atmosphere is very, very thin. Now, another area where things in front of other things were important in solar system exploration was looking at the ring systems of other planets. Now, Saturn has such a big, bright one, it was discovered right away. No surprise. Jupiter has a very faint ring system. It wasn't seen until Voyager 1 flew by Jupiter. But did you know that Uranus, Neptune, and other bodies have rings too? Well, they do. And this is the data that led to that discovery for Uranus. We had an airborne telescope aloft looking at Uranus occult a faint star. Occultation is when a bigger object goes in front of a smaller object. And the idea was they were going to do the same things that they did with Mariner 4. Look at the attenuation of the light coming from that star as Uranus passed over it to gauge how dense Uranus's atmosphere was. But what they found was, and this was back in the days of strip recorders, there were 5 little dips in light coming from the star behind Uranus, and on the way in, and those 5 were matched on the way out. And the only way that could happen was if there was rings getting in the way before and after. This is the sketch, or the scratch pad, on which the discovery telegram for this finding of Uranus's rings was made. It's one of the artifacts that I like the most in all of the National Air and Space Museum's collection. You can see the crossing out, and the person who's writing this, who made this discovery, recognized it right away. He was so excited he could barely contain himself. And variably leaping from this page is the excitement of that discovery from Uranus going in front of another thing. The same thing happened at Neptune. We found that Neptune had a ring system also because of little dips in the light of an object behind it as Neptune passed in front of it. And Neptune is not the only body in the solar system that we've used this method to determine as a ring system. Charlikle and Chiron and Haumea are either asteroids or trans-Neptunian Kuiper belt objects, and they all have faint ring systems that we've discovered this way, probably debris kicked off their surface by an impact of another body. Another thing that we can tell about these outer solar system bodies is their shape. If a number of ground stations have the same timekeeping and are observing very accurately as an unseeable asteroid passes in front of a star, if you plot the location versus time, you'll end up with a hole that gives you the shape of that blocking body. So we're discovering a lot of things about our solar system because things go in front of other things. But wait, there's more. We use the same tactic to look for exoplanets and, in some cases, even the ring systems associated with exoplanets. Our technology is good enough for us to see those little dips in light that reveal these features. And even more. If you look at the dips in different wavelengths, just like the wavelengths being found for helium, the lines in the spectra, the way different colors are affected when an exoplanet passes in front of its star reveal what the chemistry of the atmosphere is. Let's contemplate that for a minute. We actually now have the capability of not only detecting planets around other stars, we can tell what their atmosphere is made of. How's that for cool? Now, Einstein was vindicated when Eddington measured the deflection of starlight going around the edge of the sun. But Einstein's ideas operate at much larger scales. Instead of starlight, imagine if you had a very bright galaxy, a quasar, something like that, and it's sending out light, and there's a lot of heavy material, a black hole, a cluster of black holes, even a galaxy in the way. The gravity of that intermediate body can deflect the light and focus it like a giant lens so that it actually comes down like this, bends, and comes to us. And what we see from the ground when that happens is a view that looks like this. This square now is blown up to here. This galaxy is the bending body. Its cumulative gravity is deflecting the starlight of an object behind it. And we see, just because it's coming now bent, we see an image of what's behind it. Here, 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 and here. This kind of thing is called an Einstein cross in recognition of the person who first figured out what was going on. Now, that's enough about things going in front of other things for the astronomical research successes. Let's go out and see what happens when a thing, the moon, passes in front of another thing, the sun. But remember, as you do so, you can learn a lot by studying things going in front of other things, if you're an astronomer. Now, if you're putting things on top of other things, not so much. It's kind of silly. Thank you very much. I hope you enjoyed the presentation.